Hey guys, we're going to go through the notes for free fall. All right, so this is from your packet. I just kind of redid it on the board here, and we're going to walk through solving a free fall type of problem. So another way to say it's just a dropping problem, right? And so if I took a ball, took something like this, all right, I had it up here and I just dropped it. Right? What can we actually calculate about it? Why is it actually dropping to the ground? All right, we can actually determine how fast it's going after time has passed and the type of displacement that has occurred as well. So we're going to walk through each of these and say, all right, my time is going to be 0. We're going to try to figure out my velocity. All right, so something to keep in mind is when I'm dropping something, how fast is it moving right now? It's at rest, it's 0. So my initial velocity, all right, is going to equal 0. All right, my time is given to me as 0. I don't know what my final velocity is. What's my acceleration? And now going through the reading and talking with other things, in other videos, we're going to use 10. Now, 9.81 meters per second squared is the actual acceleration due to gravity. But we're going to just round it up to 10, makes things a little simpler, and doesn't really affect things. We're not engineers creating stuff to where we have to account for it exactly. We're still trying to learn and understand the concept. So we're going to use 10. Now, we also have to determine which way is positive and which way is negative. And right now, the dropping problems, it might not seem like it matters, but soon, and a unit from now, not next, the one after, projectiles, we're going to not just take things that drop, we're going to take things that fly up in the air and then come back down. We're going to take things that fly at an angle. All right, and so we have to account now, we have things in both directions. So we have some things have to be positive, some things have to be negative. I have found that the best way to just be consistent across the board with these problems is to make down negative. You kind of tend to intuitively understand that anyway. Up is positive, down is negative. So every dropping problem, okay, we're going to have an acceleration of negative 10. All right, negative 10. So we can solve every one of these problems the same way. All we do is change our time by each of them. All right, so what equation are we going to use? We have all these things. This seems like the simplest equation to use. That accounts for everything that we have. All right, so we can't really see those very well. All right, so now my final velocity I'm solving for. My initial velocity is 0. My acceleration is negative 10. My time is 0. All right, my velocity is 0 meters per second. That's my answer here. All right, we use the same equation. All right, my final velocity, I don't know. My initial velocity is 0. I have negative 10. Now my time is 1 second. So my final velocity is going to equal negative 10 meters per second. So after 1 second, that ball is going to be traveling at negative down 10 meters per second. All right, and we continue to do the same thing. All right, VF equals 0 plus negative 10 times 2. Oops. So my final velocity is going to equal negative 20. You should be starting to see a pattern here. It's going to get faster by 10 meters per second every second. So after 3 seconds, do the exact same thing, you get negative 30 meters per second. After 4 seconds, you get negative 40 meters per second. And after 5 seconds, you're going to get negative 50 meters per second. All right, so you see it increases, right? Because that makes sense. Acceleration is for every second, the velocity changes by, in this case, 10 meters per second. Negative is going down because it's dropping, so it's going to be changed by negative 10 meters per second. So we go 0, then negative 10, negative 20, negative 30, negative 40, negative 50 after 5 seconds. But now we want to figure is how far is it actually falling during that time. All right, so we're looking for the displacement. All right, so in this case, we can use my initial velocity is going to be 0. Don't know what my final velocity is. Not sure. All right, my acceleration is -10. Okay, we got my this velocity 0, 10. All right, time in this case is equal to 0. So if I take my displacement, which is what we're trying to find, equals my initial velocity times time plus 1/2 at squared. All right, I don't need to worry about my final velocity. I've calculated that over here, so I could use it if I need to. But in this equation, I don't need to. All right, so my displacement equals 0 times 0 plus 1/2 -10 times 0 squared. All right, obviously, if I haven't dropped it yet, it hasn't moved. Makes sense, okay? So same equation. Plug the numbers in now, 1 second. So again, displacement equals 0 times 1 plus 1/2 -10 times 1 squared. So 1 squared is 1 times -10 is -10 times 1/2 is -5. So it has dropped after 1 second, -5 meters. Again, negative just tells me downward. All right, so if I had the ball and it dropped, let's say after 1 second, it was right here, and that was 5 meters. And the negative just tells me it was downward. All right, so we do the same thing for the next one. All right, same equation. A naught t plus 1/2 at squared. All right, 0 times 2 plus 1/2 -10 times 2 squared. All right, so my displacement equals 2 squared, which is 4, times -10 is -40. Half of that is -20. 0 times 2 is 0, and so we get -20 meters. All right, so you see, after 1 second, drop 5, but then 1 more second passed, and now instead of just dropping 5, drop 15 more. All right, because accelerating is occurring, is increasing that velocity. That's what helps get us a curve on a position time graph. All right, so we just plug in for the next one. Now we should notice that, all right, that's 0 because it's a dropping problem. All right, so that gets eliminated. Plus 1/2 at squared. So it's 1/2 times -10 times 3 squared. 3 squared is 9 times -10 is -90. Half of that is 45. So equals -45 meters. All right, so to kind of go a little faster, 1/2 at squared equals 1/2 -10 times 4 squared. 4 squared is 16, -160. 1/2 of that is -80. So now my displacement equals -80 meters. And then the same thing down here. After 5 seconds, 1/2 at squared. 1/2 -10 times 5 squared. 5 squared is 25 times -10 is -250. Half of that is -125. So my change in x equals -125 meters. All right, so you can see, drop 5 meters the first one, drop 15 the second one, drop 25 the third one, 35, 45. So it increases more and more and more displacement each time. And we see that because we're identifying the actual position or the total amount that it had dropped. So after 5 seconds, it dropped 125 meters downward, and that's what the negative says. All right, so this is what should kind of be understood in the notes. It's getting faster and faster and faster and faster and faster. So I'm dropping more and more distance every second. All right, now let's take a look at the graphs to account for this exact problem because they look a little different. All right, so erase this guy. We're going to do a position time, velocity time, and acceleration time graph for a dropping problem. All right, so make sure we're remembering the details, meaning if we have a an xt graph. We got a velocity time graph. And then we have an acceleration time graph. All right. If we're looking at something qualitatively, okay. Now, should probably not have this guy so close. We'll get to that in a second. So my displacement. We said if we look back at those numbers, we see it was -5, -20, -45, -80. It's all negatives, which is down here. So this is where I stopped in my origin. This is the beginning point where I dropped the ball. And my displacement is becoming greater and greater. And so I'm going with the curve, tells me there's acceleration. And since my displacement is further and further away downward is negative, okay, and I'm getting faster and faster, I'm covering more and more, okay, I'm getting displaced more and more every second, it curves, and it curves downward. Again, this is telling me position. It's negative. So if I know this is negative, right, and if I took little tangent lines of each of these, all right, it's going about like that, it's going about like that. It's got a negative slope. I'm speeding up, as we saw with the data, speeding up, and it's in the negative direction. So this is negative. So it's going to be just like that. I'm getting faster and faster because this is 0 meters per second right here. And I'm getting further away from that, meaning I'm getting faster and faster in the negative direction. All right, so now I take a look at my acceleration time graph. All right, positive, negative. And what is my acceleration? It is acceleration due to gravity, and it is -10, and it is constant. So it's going to be a horizontal line. So a dropping problem, as long as down is considered negative, okay, that's being held there and then dropped, right? It's going to have a curve going downwards. This is getting faster and faster in the negative direction. If I took the tangent lines, I would get a negative slope, which tells me that I have a negative velocity. It's getting faster and faster, so it's going away from the line. And then we know that my acceleration is -10 because it's gravity. So it's going to be a constant acceleration here, and that's what this would tell me. Negative slope, negative acceleration. Same signs, remember our rules, same signs mean I'm getting faster, which is true. You drop something, it gets faster and faster and faster. Now, one little caveat before we finish. If you just kept going after 10, 20, 30, 40, 50, 70, 80, 100 seconds, it's going to be going at some astronomical speed. We kind of all know that if something dropped out of a plane, or if you're skydiving and you jump out of a plane, you're going to be accelerating, getting faster. But then at some point, you hit something called the, do you know the word? Terminal velocity. Terminal means the end, meaning that you are now moving at a constant velocity, meaning you're not accelerating anymore. Still moving downward, right? If you ever skydived or seen something, it's still moving downward, but it's moving at a constant velocity. And there's reasons for that called drag or air resistance, so that as you're falling, you're making contact with all these individual atoms in the air. And based off of Newton's third law, which we'll get to, equal and opposite reaction. So you hit it, it hits you back. All right, and so enough of those are hitting you that the actual force that is bringing you down is being countered, and it gets to an equilibrium. So you just move at a constant velocity. That's bringing in concepts from force and other things that we're going to get to. But in reality, yes, you will eventually slow down to a constant velocity, and so you will not have an acceleration anymore because of air resistance. We're not accounting for it because it way complicates things. You have to take in area, humidity, the density of the air, the fluid that you're moving through, and all these things that, okay, you don't need to do. And we're not going to do it. So we're going to understand that, yeah, if we actually took an object and dropped it, it wouldn't get those exact same speeds. It would be a little bit less than because of air resistance. But we're just going to ignore that for now and calculate it as if it is not there. All right. Hopefully this makes a little bit of sense. Rewatch it again. Make sure to ask any questions if you are uncertain. All right, thanks guys.